Welcome class. This is our lecture number 4 on properties of Laplace transform. In the previous lecture, we have derived 6 properties and taken some of the questions asked in civil services. So let's get started with our 7th property. If ft is a periodic function with period t, then Laplace transform of ft is equal to 1 by 1 minus e to the power minus st integral 0 to capital T e to the power minus st ft dt. This is a very important property and we are going to prove now. We know that Laplace transform of ft is equal to t is equal to 0 to infinity e to the power minus st ft dt, and we know that any definite integral, we can change the variable. We can write it as u is equal to 0 to infinity e to the power minus su fu t. Everything seems perfect. Now we are going to write it like this. We are going to use this one, and we can say that u is equal to 0 to t plus u is equal to t plus 2t, because we are breaking it into the periods, plus till u is equal to n of t to n plus 1 t, and we will put the integrand now, e to the power minus s of u fu du. Similarly here, e to the power minus fu su fu du plus e to the power minus su fu du. Now we can readily see that we have introduced in the last one n. So since this is a periodic function with t, we can write f of t is equal to f of t plus nt is equal to fu. Please highlight this point because we will be using it later also. So we have introduced this, so we can use over here as we can use a summation that runs from n is equal to 0 to infinity and integral u is equal to nt to n plus 1t e to the power minus su fu d. Fine. Now we can easily see that why have we used this summation. I will try to explain this. If we put n is equal to 0 in this integral, this becomes u is equal to 0. U is equal to 0, and here 0 plus 1, 1 t. So u is equal to 0 to 2. This is the 0 to t. This is the first one. Then if we put n is equal to 1 over here, this becomes u is equal to t, and this becomes 2t. T to 2t. Similarly, it goes to 0 to infinity till last. So we have used the summation because we are adding it up. Now we will put u is equal to t plus n capital T, and this is a substitution we are going to use. So if we take the derivative, du is equal to dt. Now see, we are using it here and we are converting into t. Again, when u is equal to nt, then what it becomes? If we put into this equation, nt is equal to t plus n of t. So t becomes is equal to 0 because this one get cancelled. So we are having the limits for this one. So when u is equal to n plus 1 capital T, then nt plus t is equal to t plus nt. Again nt get cancelled, so we get our limits as t is equal to capital T. Now we can use it in this equation. This is summation n is equal to 0 to infinity, and our integral limits are t is equal to 0 to capital T, e to the power minus s. What we are going to use for u now? T plus n of t here, and f of u we can write f of u as t plus nt also. We can write it as t plus nt fu. So we are talking in terms of t, so we can use it directly. And we have seen that du is equal to dt. So this becomes perfectly fine. Now let me erase the upper props. And copy the integrals. So this integral is n is equal to 0 to infinity, and if we see here, if we take e to the power minus s and capital T outside and put into this block and take it as 1, and second integral 0 to t capital T e to the power minus st ft dt. Okay, now we have studied, if we try to break this one, what it becomes? It becomes, if we put n is equal to 0, this becomes 1. Then what it becomes? If we put n is equal to 1, e to the power minus s of t. Then if you put e to the 2 value as 2, it becomes 2s2, similarly till infinity. Now we can see that exponential is always positive. So if this goes into the denominator, that means it is less than 1. So this is a geometric progression that we are going to use right now. And we know that for any geometric progression, n is equal to 0, a r n is equal to r to the power n is equal to a by 1 minus r, where mod r is less than 1. So this completely follows the property. So our first term is 1 and r is a common ratio. That is, common ratio is e to the power minus st. If we divide e to the power minus 2st by e to the power minus st, that becomes again same. Similarly it goes on. So we are very clear with that this is our common ratio. And if we put it like this, we get our value. So this is what we have proved, and this was our claim over here, and this is what we have finally proved. Okay, now this is the question, and this question is about the use of finding Laplace transform of a periodic function, and we are taking the question from previous year papers. This was asked. So first I will try to plot this function. This is time scale. This is the function ft. I take this one as pi, 2 pi, 3 pi, 4 pi, and so on. For that, let me first start evaluating from the initial points. When n is equal to 0, what we get as ft? We put n is equal to 0 here. So this becomes 0. This becomes 0 plus 1, pi. So our time varies from 0 to pi. Alright. And what is the value? The value is 1, as we can see. Now, in this one, if we put n is equal to 0, what becomes? Pi. So t ranges from pi to 2 pi. Let me erase it. So this range from pi to 2 pi. What is the value? Minus 1. So this is the case when we have referred for n is equal to 0. Before we go and find others, let me first plot this one. N is equal to 0. For 0 to pi, what is the value of function? 1. So we plot 1 over here. So this becomes our function. Value point. From pi to 2 pi, what is our function? Minus 1. So we go on the negative axis, and if we plot minus 1, it becomes here. Now, when n is equal to 1, what will be the ft? For this case, ft is going to be, if we put 1 here, what do we get? 2 pi, and here 2 plus 1, 3 pi. So range is 2 pi to 3 pi. And what is the value? Value is again 1. Similarly, jab we are going to put here 1, what it becomes? It becomes 2 into 1, 2 plus 1, 3. So 3 pi to what becomes? 2 plus 2, 4 pi. So we are seeing what is actually happening. The function is repeating. The function is repeating with periodicity. So from 2 pi to 3, again it repeats. From 3 pi to 4 pi, again it is minus 1. So now we have to find the period. To find the period, we have read the cycle. From where the cycle starts. Here the cycle starts here. And where it again starts? It starts at this point. So we can say that period is 2 pi. There is no doubt about it. Now we are going to use the Laplace transform for this function with the property that we have just now studied. 0 to t. T is the period. E to the power minus st ft dt. Alright. So here the period is 2 pi. So in place of capital T, we can put 2 pi and s. And t is your 0 to 2 pi. E to the power minus st ft. We have to break this into two components. Why? Because the value are changing from 0 to 2 pi. From 0 to pi, value is 1. From pi to 2 pi, value is minus 1. So if we further bifurcate, our integral becomes 0 to pi e to the power minus st. And here what is the value? 1. There is no doubt about it, and it is pretty much clear. Similarly, from pi to 2 pi, what we get? E to the power minus st. And what is the value from pi to 2 pi? Minus 1. So this is our integral. All we have to do is just solve this integral. Now I will rub this diagram so that I can solve this. Okay. So our integration becomes 1 by 1 minus e to the power minus 2 pi s integral 0 to pi e to the power minus st d of t plus pi to 2 pi e to the power minus st minus 1 dt. We'll close the bracket. Alright. Now this becomes what? If you take the integration of this one, it becomes e to the power minus s of p divided by minus of s, and limit runs from 0 to pi. Here we take the minus sign outside and the integration is same, so minus minus will become plus. There is no doubt about it, but it limits, mind you, is different, that is from pi to 2 pi. So if we just put the limits. First we put the limit as pi in terms of t. What it becomes? It will become e to the power minus s pi s minus minus become plus, and we put 0. So e to the power 0 is 1. Similarly over here, when we put the value of t as 2 pi, so e to the power minus 2 pi s divided by s minus sign e to the power minus, in place of t we put pi. So we are getting the answer. We can see one thing, that s is common, so we can take them outside. S is outside, and we can see that e to the power minus 2 pi x minus 2 e pi x plus 1. This is a perfect square. If we can write it as e to the power pi x into 1 minus e to the power minus pi x, and if we write it like 1 plus e to the power minus pi x square, there is minus sign because here it is minus, so we have to write it minus over here. So this one term will be cancelled, no doubt about that. And what we get is 1 plus e to the power minus pi s, and 1 minus e to the power minus pi s. Okay, so we have to be very particular about our calculations, because if it is plus 1, then obviously it is 1. So we have taken as a mistake here, so we must rectify it right away, and we proceed. What we do, we multiply both sides by e to the power pi s by 2 and divide the same. 1 minus e to the power minus pi x divided by 1 plus e to the power minus pi x. Okay. Now, if we take that one inside, it becomes what? E to the power pi s by 2 minus e to the power minus pi s by 2 divided by e to the power pi s by 2 plus e to the power minus pi s by 2. Alright. Now, we can write it over here as 1 by s e to the power pi s by 2 minus e to the power divided by 2 and e to the power pi s by 2 plus e to the power minus pi s by 2 divided by 2. This is the sine hyperbolic and this is the cos hyperbolic. So what our answer becomes? This becomes sine hyperbolic pi s by 2 divided by cos hyperbolic pi s by 2. So our answer is 1 by s tan hyperbolic pi s by 2. So this is the answer, and this was based on the periodic function Laplace transform. Thank you for watching.